My name is Wilfred Abincha. I'm going to take you through this tutorial. Kindly subscribe, like. I'm going to share my knowledge on the concept of genomic selection in this tutorial. Then hereafter, I'll also make another tutorial on how to implement genomic selection in R with examples. Genomic selection is a tool that is used by plant breeders and animal breeders to estimate genomic estimated breeding values based on genotype and kinship. So breeders will select individuals that have high genomic estimated breeding values. In classical breeding, breeders assemble their materials, then evaluate them and select materials with high values. Then cross these materials, plant them and evaluate them. When they do that, you find that the mean has shifted, as it has shifted from cycle 0 to cycle 1. However, in classical breeding, this work here is very intense. When we look at the breeder's equation, to improve genetic gain over time, it needs this T, years per cycle, to be reduced. And it's very hard to reduce this T in classical breeding. Therefore, we need a system that can reduce T. Also, R, this is a selection inaccuracy, has to be increased. We know there's things that has to be done to increase selection accuracy, including evaluating your materials across many locations and seasons and in many replications. And this requires a lot of resources that most research institutions don't have. Also, to increase selection intensity needs a lot of resources, because to have a higher intensity means you have to be intense in your selection. And when you are intense in selection, it means you are going to select very few materials. And if you need to select high number of materials, but also have high intensity, it means you have to increase your breeding population so that your breeding population is so large. And when you select some materials, some reasonable number of materials, your selection intensity is high. And that translates to a lot of time, money, and other resources. Now here, genomic selection comes handy because it can increase the rate of genetic gain over time by reducing this time by cycle. Also increases this accuracy. When it does that, the rate of genetic gain increases. So to carry out genomic selections, you have to develop genomic selection models. You develop a training population here, also known as a reference population. You genotype this population and phenotype. Your phenotype has to be a very good estimate. And from this genotype and phenotype, a model is made. You train a genomic selection model, and now you come to your breeding population, you genotype, you only genotype. Then using this training model, you compute genomic estimated breeding value from these genotypes and select your individuals that have high GEBVs. These selected materials are few. You can phenotype them and include them here in these materials here and retrain your model to make this model more robust. That is the concept behind genomic selection. When you have this model, you don't need to phenotype your material. The only thing you do is just to genotype. We know that quantitative traits are complex because they are controlled by many genes, and the variance due to each single marker in quantitative traits is very small. We need a system that will select individuals based on all markers, because quantitative traits are controlled by many genes. It has been found that a genome of individuals have large variabilities, and the most abundant form of variability is SNP. For example, this is an individual. There's variability here between individual 1 and individual 2. This is called a SNP. Assume that this is a genome of an individual, and this is a marker, and this is a QTL. These markers are at linkage disequilibrium with the QTL. For example, this marker 3 here is in linkage disequilibrium with this QTL. And if this allele at this marker is capital TT, a value of 0 has been found that is associated with this QTL. But if it's capital T and small t, a value of 10 is found. That means this value of 10 is due to this small t. If we substitute this capital T here with another small t, we have two t's, another 10, value of another 10 is added, making it 20. That means the value of this t allele is 10. That's average effect of allele substitution. That's why we have said X, this X marker 3 has an effect, a marker effect of 10. To compute genomic estimated breeding value, you calculate or you sum all the marker effects. That's why you see this is a marker Xi and effect Gi. When you sum all these marker effects, you get your genomic estimated breeding value. Let's look at the genomic selection linear model. As I said, it looks like this. This is the mean here, and this is the marker, and this is marker effect, and this is error. This is a vector of error. Making this kind of model is not easy because we have an issue called the curse of dimensionality. This is where we found we have more parameters than data points. For example, ideally we have so many SNPs than genotypes. Like you can have 40,000 SNPs and only 400 genotypes. This leads to over-parameterization. An over-parameterized model is not reliable, does not give you good estimates. So this has been called the curse of dimensionality. And it can be solved by using regularized correction. These regularized correction are labs. They shrink the estimates, or they use variable selection of markers, or they can employ both. This regularized correction imposes a penalty to restrain the vector across all markers or on variable markers. When these penalties restrain the vector across all markers is called ridge regression. This here, ridge regression, a constant is developed. This constant here is developed and it's imposed on all markers and it shrinks the marker effects. Every marker is shrinked by this constant here that does not change. We also have lasso and Bayesian. Lasso and Bayesian, they apply this constant but variably, not on all markers. So to get this constant here, data sampling is necessary. You have to compute this constant here. In GBLUP, kinship or genetic relationship between lines is created. And here, the genomic sequences of your material is used to create a G matrix. So the importance of G matrix is that it shows the kinship among the individuals, so that when your model is doing a computation of breeding values, it runs through those individuals and identifies those individuals that are similar or that are related and awards them similar values because they are related. So this kinship effect is helpful because it captures on kinship and also on Mendelian sampling. So here is the GBLUP. This is the effects of markers here. And this lambda here is that penalty that we impose on all the markers so that it restrains the matrix, making our estimates to be real. So this lambda here is that penalty which we imposed. And its work was to correct the curse of dimensionality. And this G here, this is a kinship matrix, but it's not from pedigree. It's a genomic relationship matrix, which tells a model that this individual and this one, they are related. According to the level of relationship, they are awarded their effects. And this G matrix is computed using the X matrix times the transpose of X matrix here divided by the number of markers. Let's look at the kinship matrix because we have realized that kinship is very important in assigning the effects of markers and consequently affects the computation of genomic estimated breeding values. We have a pedigree relationship that is captured in A matrix. So A matrix uses the pedigree relationship, and we have the G matrix which uses genomic relationship to explain kinship. So G matrix is preferred because it takes account of Mendelian sampling. So a breeding value of an individual, like this G is a breeding value of an individual, is a half the breeding value of the male parent plus a half the breeding value of the female parent. However, this only does not give, is not realistic. There's another factor here called M, which is deviation from the mean breeding value. Because this is a female plant plus a male plant, you find the mean, then you get the breeding value of the offspring. But there's a deviation, this M. It comes from Mendelian sampling. Because during meiosis, there's a crossing over which causes recombination. Recombination leads to deviation from the mean values. Therefore, this deviation is added here. And this deviation can only be captured by G matrix. Let's look, we have two matrices here, G matrix and A matrix. And we know that full SIPs share 0.5 genome because all the full SIP families got a half genome from the male parents and half from the female parents. So they share 0.5 genome. So if we have a plant 1 here, this is plant 1, 2, 3, 4, 5. And plant 1, plant 2 is offspring, and plant 4 and 5, they are from the same parents. So they share a half of the genome. Plant 3 is unrelated. That's why it is 0 here. It has a 0 value. This is from the pedigree information. But in reality, a full SIP don't share 0.5 of the genome. In reality, it's from 0.3 to 0.7. Why? This is because of Mendelian sampling. During meiosis, recombination events leads to that division. It's from 0.3 to 0.7. For example, let's look at this G matrix. This is the same individuals here. This individual here, 2, 4, and 5, they are full SIPs, but then they are not 0.5. They're not 0.5. The value is not 0.5. It has deviated. This is because of Mendelian sampling. And this individual here was not related at all. It was 0. But it's not 0. There's some small relationship, which is 0.002. The same applies to half SIPs. Here, this individual here and this individual, they are half SIPs. They have 0.25. And this one here, they are not related. It's 0. But if we come here, you find that this is 0.21, not 2.5. And this is 0.33. Though these are half SIPs, this should 0.25. This deviation is due to Mendelian sampling. This is now in reality, this is what happened. But this one does not take account of what happens in the genome of an individual. When we put the G matrix in the genomic selection model, it takes account of the Mendelian sampling, giving us reliable values, and ultimately we get reliable genomic estimated breeding values. Let's see how G matrix is computed. For example, if we have 3 individuals here, 1, 2, 3, and we have 4 SNPs, if lowercase letters represent minor alleles, which are less frequent, then we can create this minor allele frequency matrix. The frequency of having a minor allele here is 0 because we don't have a minor allele here. This one here is 0. This one here, there are 2, 1, 2, 2. Is 1 here, which is lowercase, 1, 1, 1 here, and this one is 0. The same applies to here. This 0, 0, 1. This is 1, 0, 0. That's what we have here. This is a minor allele frequency matrix. So the matrix which we computed is this one. Minor allele frequency matrix is this one. Now, if we subtract 1 from each element of this matrix, we get this matrix here called M matrix. M matrix is a very important matrix in computing Chi matrix. This matrix here is here. There's a property of matrix when a matrix is multiplied by its transpose. For example, this M matrix, this is its transpose here. If we compute this, we get this matrix here. This matrix is this one. This is number 1, 2, 3. This is individual 1, 2, 3. We have diagonals here. Diagonal represents the number of homozygous loci for each individual. This individual here, 3. It has 4 homozygous loci. And outside here of diagonals is the number of alleles shared by relatives. This individual 3 here, in SNP 1, it has 0 alleles shared by relatives. In SNP 2, 0 allele. When we come to individual 2 here, in SNP 1, it has 1 allele shared by relatives. The same applies to this here. You can see when a matrix is multiplied by its transpose, it gives us some information that is related to kinship. Keep that in mind. Now let's look at P matrix. P matrix has allele frequency expressed as this one here. This here is minor allele frequency. For example, if we have individuals with locus 1, 2, 3, 4, and these are their minor allele frequency, if we place 0.4 here, 0.04 minus 0.5, it gives us negative 0.1 times 2, it gives us negative 0.2. And if we take this 4 here, 0.1, it will be negative 0.1 minus 0.5 give us negative 0.4 times 2, it gives us 0.8, and this applies here, and we assume that it's the same for individual 2, 3. This leads to us having this kind of matrix here, which is called P matrix. To get X matrix, what we do is M matrix minus P matrix. This M matrix, you remember the M matrix which we computed, minus the P matrix, it will give you X matrix. And X matrix, it gives more credit on a rare alleles, more credit given to rare alleles. One thing you need to know is that, as I said, if you multiply a matrix by its transpose, it will give you some form of kinship information. So to get the G matrix, is this X matrix times its transpose, it will give you some kinship information divided by the number of markers. This here, this equation here, it scales the G matrix to be somehow like an A matrix so that you get your kinship. So here is our formula of getting a GBLUP, GBLUP. These are marker effects, and this is a lambda which is used to correct the curse of dimensionality, and this is our Chi matrix which take care of kinship, so that the model will just look at those individuals that are related and give the marker effects according to the value of the kinship. And that is the concept of genomic selection. It's very simple. And wait for the other video where I'll be implementing genomic selection in R, and we will have real examples. If this one is helpful, kindly subscribe.